All right. Good morning, everyone. Let's get started today's class. So before we actually start working on code, I just want to talk about two quick things here. So one is just a reminder that assignment number 4 is due today, 11:59 p.m. And if you, some of you have already submitted, so thanks for that. And if you have not, make sure to submit before the deadline. And also, something that, so in the, Thursday and Friday of last week, I was working with different students and trying to troubleshoot that animation issue. And it was just, kept running to different issues. And because I wasn't able to reproduce the error on my computer, it was also more difficult for me to find the solution. So at that point, I was ready to just delete the chunk and, if you're having issues, and keep going. But then, something that Shakar actually said in class, and I understood that he was just referring to something else, turned out to be the solution, at least for some students that I was helping. So it seems like, as again, Shakar found that out. So thanks, Shakar, for really working on it and digging. I would really appreciate that. The piece of the code that was causing the issue was when we were trying to add the county labels. So by removing that, you don't get the error, but then it produces a whole bunch of PNGs, right? Which is not the goal. And then again, Shakar also identified that if you install a couple of other packages, or maybe just one, but I did two and it worked, then you are actually able to combine all the PNGs into a GIF. So the bottom line is, if you have not tried it yet on your, if you're having the issue of creating the animation, either because it was giving you the error, or because it was not combining the PNGs into a GIF, give it another try by removing that the piece of the chunk or the piece of the code that adds the county labels, and then install the packages that are needed to combine the PNGs into a GIF. And I think that at that point, you should be able to create an animated GIF, of course, without the labels of the county labels, but that's better than no GIF at all. And with that, I'm assuming that everyone would be able to create the GIF. And therefore, I would expect for everyone to produce a GIF for the mini project as well. So if you have not, we talked a little bit about this on a GitHub issue in our repo. It's called, the issue is number 18, and the title of the issue is Still Having the Same Issue. So if you open that issue and you browse, there are some instructions, some links there for you to try this on your side. And if for some reason you do all that and you're still having issues producing the animation, let me know. I'll be glad to help you out. But I think that's the workaround that would solve most of our issues, as far as how many of us were not able to reproduce the animation. All right, so let's get going with today's exercise. I did send an email last night with some instructions, which was basically just telling you that I had uploaded to GitHub a data set and a partial code, and I was asking you to download those and then create a new project on your computer using those files. So I'm not going to take the time to do that today or in class, because I did ask you to do that before class today. So I'm assuming you already did it. But just to do a quick overview, this is my main folder of the class. You should, if you follow the instructions on the email, you should have a 04 EO monitor folder at this level. If you go inside that, you should have your code, data, and output folders. Where in the code, so I have more stuff than you do at this point, but on the code data, you should have the 0206 EO17 wrangling partial, which is what we're going to develop today. And under data, you should have the EO17.csv. And also you should have created the project at this level, right? So at the main folder of the project, so not inside code, not inside data or output, but right here. And so this is what you should be seeing. I'm going to assume that you did this, and if it did not, I guess you're going to have to catch up. All right, so let's get started. If you can go ahead and launch this project. You can just double click on that R project to launch it. Okay, so this is what it should be seeing again. If you launch the proper project, you always check that you see that project name on the top right. Check on the files tab that you have that you are at the right level of the project. Also, you can go inside the folders and make sure you have what you copied and pasted there. And also just want to point out, so for some reason, I don't know if this happened on your side, it didn't used to happen on my side, but like the environment is not appearing. So if you just push, I think, let's see, yeah. So one of these buttons here, that makes your environment appear if that's also happening to you. Okay, so let's get started with today's code. So today, the objectives of today's class is to talk about the role of yield monitor data in agriculture. Then we're going to import yield data, explore it with tables, plots, and maps. So do some exploratory data analysis, and then learn and implement some new data wrangling tasks that are specific to geospatial data. Okay, so I guess before we really start the code, I just want to mention this. I think is if you have already submitted the assignment, then you already have a pretty good grasp of why we should be cleaning raw yield monitor data. And I guess one thing I want to comment that I thought was really interesting when I heard this. Someone said in a conference, I don't know the reference to tell you who said it or what. I think it was the International Conference of Precision Ag, but someone important, I don't know who, said the following: yield monitor data is both the entry exam and the final exam of precision ag. And if we just stop to think about it, why that is and why that sentence makes so much sense. So if you go to work with a producer, or maybe you're doing research on a farm scale that you have with yield monitor data, one of the first things, especially if you think of a producer setup, that you can, one of the best layers that you can use to first assess yield differences within a field is a yield map, right? Is yield monitor data map, because that's going to give you a really, really good idea of how yield is varying within a field. And so by using that layer, you can really learn, okay, I have this part of the field here that is yielding lower, perhaps consistently year after year. There's other part of the field that is consistently yielding high every year. And there's this third part of the field that maybe in some years yields high, other years yields low. And then that really, helps you to understand, or to really see how yield is varying, and then to try to come up with some understanding of what is causing those yields to be high, low, or variable across years. And then that is really what gives us the insight to say, well, maybe here is low pH, or maybe pH is too high, or maybe nutrient is too low, or maybe something else. Maybe it's just elevation, like you have a lower lying area of the field that accumulates water, and on wet years, the crop doesn't survive because it's waterlogged. So that really helps you to understand, trying to understand what is causing that variability. And then on top of that is when we make recommendations, if possible, to overcome whatever it is causing lower yields, especially. And once we implement those solutions, then next year implement that solution. So let's say it was low phosphorus in the soil, and then you just apply phosphorus to the level that it should be for maximum plant yield. And then next year you harvest that field, and then you see again if your intervention had an effect, right? So it's both the entry exam, but also the final exam of precision ag. So it's a really powerful data source in precision ag. And the first step for us to make good use of this type of layer is to actually clean it, because it comes with a lot of potential errors that we should remove them before we actually use that layer for any decision. So all this, as far as what errors may be caused, you're going to read more about on the reading assignment that's due tonight. So I'll leave that especially for the class on Wednesday. So let's get started with the code here. I already left you the setup chunk all done. So please go ahead and run that chunk. If there's anything here that pops up and says you don't have a given package, you know how to install it, please go ahead and do it on your side. And also, I just want to mention something quickly here. So when we're using Quarto files, we can define like global options that we want to have an effect on all chunks at the YAML level. For example, right here, I'm asking for the chunks to not show a message or a warning. However, this only has effect when you render it. So when you render, if a chunk produces a warning, like tidyverse produces a warning every time that we load it. I guess I didn't really load tidyverse directly here, but some packages when we load them produce a message, right? Which is kind of annoying. So you can control that at the chunk level by using the following. I left this for you, but the following syntax, which is hashtag pipe. Then if you hit tab, there's a whole bunch of options you can change. So what I did here was just to change the message to false. So if any package in this chunk only produced a message or a warning, it would be suppressed. Just to give you an information there. Okay, so let's import our raw yield data. So if you come to the next chunk, you give the assignment symbol, and we're going to use the read_CSV function, open and close quotation marks. We need to get outside of the code folder, inside the data folder, and we're going to bring in the yield17.csv. You can run that, and we can print it just to have some idea. So before we start talking about what this data, what is in this data frame, I just want to make clear something very important for all of us here. So this yield monitor data file is coming to us as a CSV. Okay, so that may be a very common file type that comes to you from a producer, for example, that sends you yield monitor data. It may come as a shape file, but I guess CSV is one of the common ways to come in. And I just want you to really think about the difference between the file that we're importing and the object that we're saving that into in R. So we're importing a CSV and we're saving that CSV into yield17, and yield17 is just a data frame, right? So it's not a CSV file anymore. It's just a CSV that stores the information, or sorry, it's just an object that saves the information of a CSV file. And this distinction is going to become important towards the end of today. So that's why I'm bringing this up now. Okay, so if we look here, let's just quickly explore this data set. So it has about almost 32,000 rows, where each row is a point in the field that yield was recorded on the yield monitor of the combine. So we have here some columns called FID, region, heading, elevation. So elevation is going to be a good one for us to think at like in the future. Distance, duration, speed, fuel usage, moisture, mass, cotton. It was cut down the name, so I don't really know what was the full name. Width of the combine, engaged, mass yield, wet yield, dry yield, timestamp, point X and point Y. So let's get a summary here and just have some trying to understand what's going on. Some of the important variables here are going to be speed for sure. And then dry yield is also going to be an important one. So dry yield would be the column that we're going to use that actually contains the yield values being estimated by the yield monitor. So we see that's ranging from 0 to almost 4,000. I think this is pounds of cotton fiber. And then we have the columns point X and point Y. At this stage, point X and point Y are being interpreted by R as numerical columns. So this is not, even though this will be turned into a geospatial data, but at this point, it's not, because the columns point X and point Y are just being interpreted as numerical as any other numerical column, just to give you some of that idea. Okay, so let me just ask this. Based on what we're seeing here, what do you think would be some relevant columns that we should keep when we start wrangling this data? So I'll start with the first one. Definitely want to keep speed, because we're going to be filtering and cleaning based on speed. What else do you see here that we really need to keep? There are three others that we really need to keep, just to give you a tip.
I think coordinates, which would be point X, point Y.
Right, perfect, thank you. Was that Omar?
Yes.
Awesome, thanks, Omar. Yeah, right. So coordinates, right? We really need the coordinates. So, sorry, was someone else saying something?
Dry yield.
Dry yield, yes, definitely, right? Because dry yield is actually the main one, is the one that has the data we want. And everything else here, you know, we're not going to talk much about it, but mass yield, wet yield, moisture, speed, distance, these are some of the other columns that the combine is collecting data, and is actually, they're all used, all these columns are used to calculate dry yield afterwards. So dry yield is our main column, but there's a lot of other columns here that help the software to calculate dry yield. So just to make that point. All right, so let's get to the next chunk here. So this next chunk, we're going to explore the distribution of yield data. So I left a little bit of code there for you. So we're doing a ggplot, starting with the data frame, and I'm just putting on the x-axis the column dry yield. I want you to add a plus at the end there, hit return. Now let's call the function geom_density. Let's start with that, just so we see the density of the data points. So this, you know, you can think of it as the more points are around a given dry yield bin, the higher is the density, right? So it's just kind of like showing us the distribution of the data points. One thing to help here is if we come back to the density at the end of that line, add a plus, hit return, and I want to call a new geom called geom_rug. That can, maybe in this case, is not super helpful because there are many data points, like almost 32,000. But it gives us some indication of how many points are at a given part of that distribution by placing this vertical bar everywhere there's a data point. So we see that most of the points are distributed around, I don't know, 1,300 or 1,200 perhaps. And we do have some outliers, maybe like one data point was all the way past 4,000 pounds of land per acre, which it's pretty unreal. You know, it's very unlikely that a field that has an average very close to 1,000 can have a data point, a real, not erroneous data point that is over 4,000. Let me ask here, I know that some people in this class have already worked with cotton yield monitor data, or just cotton in general, that could just tell me, you know, what is a reasonable yield, lint yield for cotton that you've seen in your studies.
I've always kind of understood with 1250.
1250 is going to be kind of a ballpark average, but anything under 2,000 is going to be pretty realistic.
Right. Have you seen anything above 4,000 in the past?
I've seen spot plots get over 3,000, but I've never seen anything field get over about 22.
Right. Oh, that's awesome. Thanks for sharing that. And that's, you know, that's what we're going to be seeing in the data that we're going through today and in the next classes, is that's probably around what this field in different layers also we observe. So I just wanted to bring that discussion up just so we you know, of course, it's useful when you're going through yield data, yield monitor data, if you have some idea of like what is a reasonable value, what is not. So probably 4,000 here is an error, right? So I just wanted to show this density plot for us to appreciate, you know, how easily these errors get in, and then we're going to address that later. Okay, so the next plot here is going to be the same plot, but instead of yield, I want to plot speed. So a couple of things that I notice here. So one is, you know, there is most of the speed values are probably around 4 point, what would that be? 1, 2, 3, 4, 5, 6, 7. So 4.7 is kind of the peak. The next thing I see from this data is if you look at the geom rug results, they're all binned. So they're all at the like 4, 4.1, 4.2. There's nothing in between, for example, 4.0 and 4.1, right? So probably the speed was being recorded at those intervals. So it's not really a fully continuous variable. It's more like, and I mean, it's not integer either, but you can see how it's really bent, like that there's no speeding between these breaks. And something just interesting to think about here is yield is being estimated, right? So yield is being estimated by how much cotton lint is coming in, what's the speed, how much of the header width is being filled with plants, speed, other things as you saw in the paper. So yield is being estimated, and we do expect to have erroneous estimations of yield. Speed, on the other hand, I mean, it's being measured, but it's not being affected by all these different things that yield is, right? So we wouldn't really think that a low speed value is an erroneous speed value. It's more in the sense that a low speed value has effect on yield estimation. So just to give you that idea as well. So here we're not looking for erroneous speed values, just speed values that could be causing erroneous yield values.
Sorry, Professor.
Yes.
Yeah, I don't know what's happening on my graph. I'm using the same code as the ones typed over there, but when I run it, I don't see the x-axis.
You don't see the x-axis.
Yes, on the graph.
Okay. So I don't have a good, like right off the bat, potential explanation for that. So maybe let's touch base at the end of the class and troubleshoot that. Is that okay? Okay. All right, so if we just keep going here, let's just map these yield values now. So I didn't leave any other code for you because I want us to think through this together. So we're going to start off with the ggplot. So the first thing we give it is the data frame name, right? So that's yield 17. We add a comma. Now at this level, we're going to call the AES function and specify X and Y. So X is going to be, I'm going to just select yield 17 and print it just so I get the column names here. X is going to be point X. Y is going to be equals to point Y. So notice how now we are giving X and Y are basically coordinates columns, right? They don't have the data, the yield data in themselves. They're just setting up the coordinate system of the plot, which is different from what we've been doing up until now. So we add a plus. Because this is not a SF object yet, it's still a data frame only. We're not going to use geom_sf. We're going to use geom_point. And here I want to call the AES function again and say color equals dry yield. And I just want to add a plus at the end and just change the scale already to a colorblind safe scale. So change that to scale underscore color underscore virides underscore B for binned. Okay, so if we run this, this is what we get. So a couple of things to notice here. I want you to kind of keep in mind the shape of this plot, because every time we do a ggplot, what ggplot does is it looks at the minimum and maximum value of the variable on the x-axis and sets the range of the x-axis to that. It does the same for the y and sets the range of the y-axis to the range of the values, meaning that it's not like you don't have the same range on x or y, which for all plots makes sense except for maps, because maps we have a fixed reference system that should have the same range on both ends. And we're going to see this when we get to the end of today's exercise. Another thing, so I guess what I'm trying to say is just try to remember the shape of this field right now, and we're going to compare it to when we actually plot the SF, when we transform this to SF and plot it, how that's going to look different. Another thing to notice here is, so low yield is, on the with the purple, and high yield is on the yellow. One thing to notice is that we have one, maybe it's a little bit hard to see, but there's one point. Remember that is like one outlier that was all the way above 4,000 pounds per acre. And it's right there. It's that point right there. And because of that point, and because of it being so out of the curve and not like any other points near it, it kind of pulls a lot of the color from the rest of the map to it, right? So that point itself is basically the only thing in this bin that is yellow. So it's making it a little bit more difficult to visually see differences of the other points because this one is so high on the scale. So what I want to, because of that point and because of it probably being erroneous and masking the color of the other points, I want to invite you to come here, just copy this, what we did on the chunk above, come to the chunk below, and we're going to do something quick here. So I want you to delete, like just keep the AS, so delete the data frame there, give a few returns. We're going to do a quick filter here. So on the go filter, we're not saving this yet. It's just for visualization. So let's call the yield 17 here, add a pipe. I want to filter where dry yield is lower than 3,000, so we keep more realistic and can really see better the differences in the field. Add a pipe at the end, and that should connect to the ggplot coming after. So just remember again to remove the data set that we previously had here on the ggplot call. So if you run this now, so again, it's the same data, right? But look how now we can really see better differences within this field that before were kind of masked because of that high yield point that was pulling everything, skewing the color scale, basically.
Dr. Bastos,
So
can you slow down a little bit? We're having a hard time keeping up typing with you.
Okay, yeah. Was that in this?
Yes, sir.
Yes, sir.
Okay, yeah. Let me know when you catch up, and I'll just keep talking, but let me know when you catch up, and I'll keep coding as well. So, while the guys are catching up or anyone else is catching up, a few things to notice here is we have some places of low yield, right, that we can see on the field. We have some places of like better yield coming. And also something to point out is even though this map looks pretty continuous, right? So it looks like you have data everywhere. That's not the case, and we're going to see that in the next plots. What is happening here is that the yield monitor data is collecting a point estimate of yield. I don't know at what frequency, but pretty frequently in a way that it's all points. So this should be like, if you think of a shapefile, it should be a point shapefile. But there's so many points that at least right now, they look like they're all connected, but they're not. So I just wanted to point that out to you as well. Okay, was everyone able to catch up?
Yes, sir.
Yes,
We're
sir.
good.
All right, let's keep going. So a quick thing I want to do here, and just to show you, is not show you a map, but come back with a plot. So we saw the yield distribution, we saw the speed distribution, and we saw yield distributed in space. But now I want to do, you can think of like do a correlation or a regression between speed and dry yield, just to see if we can learn something from that plot. So I left you some of the code there already. We're putting speed on the x-axis and dry yield on the y-axis. You can come and add a plus at the end. First, what I want to do is create a scatter plot, if you think of it. So to do that in ggplot terms, we basically just add a geom_point. And what makes this a scatter plot is because both the x-axis and y-axis variables are continuous. If one of them were categorical, then it would not be a scatter plot, pretty much. Okay, so we see, as we know already, speed was recorded at fixed intervals of 0.1 speed intervals, and dry yield is just like a very continuous variable. It's not bent, right? So we see here that most of these very high yield points are happening at very low speeds, right? So we see that as speed increases, yield data is more confined to be within realistic boundaries, right? Of like around 2,000 pounds per acre and lower than that. And as speed decreases, so this is the speed of the combine, right? So as the combine is harvesting, how fast or slow it is going. I just want to show a quick trick here as well. So every time that we have continuous and continuous variables on X and Y, we can use a geom to add a trend line to this. So if you come to the end of the geom point, add a plus, let's call the geom_smooth to add a smooth line or a trend line to this plot. So that was the code. And this is what we're seeing is, again, we see higher yields on lower speeds, and as speeds increases, yield comes and stabilizes. Right. So if you already read the assignment, and if you already did the assignment, you probably noticed that speed, especially low, even really low or really high speeds, have an impact on the quality of the yield that's been estimated. And here we're seeing that at low speeds, we have very high yield points. Why is that? Does anyone have any thoughts on that?
Maybe it's the overlapping data, like the sensor is trying to sense data even though it has been harvested from that point.
So that could be, that is a very important source of error. But I don't think that is exactly what we're capturing right here, right? So well, let me ask if anyone else has any thoughts on this. But thanks, Omar. That was a good observation, but I guess it's just not exactly what we're seeing in this plot. Matt, do you have any thoughts on this?
I'm sorry, I had somebody stop by my office. We're collecting data this afternoon and I got sidetracked, so I didn't hear the question.
So no, I mean, the question is why are we seeing this as far as dry, like very high and probably unrealistic yield values at very low speeds of the combine?
Maybe just to try. I think maybe when the combine is maybe turning at low speed, collects a lot of information than when it is at an average speed in the intersection kind of field when it's in the field.
Yeah, so it's definitely related to that as far as like under very low speeds, there's not a lot of plant material coming into the combine to be separated and to be cleaned. And so it's just an issue of like having very little material coming in, and perhaps especially if that happens when you have lots of data points, like you're harvesting an area that has a lot of plants, and then for some reason you have to slow down very quickly. It's just that you're going a very short distance because your speed is very low, and you still may have lots of material coming through. That's when we may see these effects. And we're going to explore this a little bit more later in this exercise, but I just wanted to get your mind thinking about this already. Okay, so let's just talk a little bit about what do we need to get this data cleaned in an yield monitor data cleaning perspective. Oh, somebody posted on the chat. So Kriti said, probably with low speed or of wind, we have lower VPD and not much evaporation that provides some force to extract water from the soil to use it for better yield, I guess. So Kriti, I think what you're saying can be important more for like generating yield in itself. But here we're really thinking of speed of the combine, right? So it's not necessarily wind speed, but it's how fast crop is being harvested by the combine, how fast the combine is moving through the field, and how that speed can have an effect. But thanks for sharing your thoughts. Okay, so definitely we need to clean this data, right? I guess that's pretty established. We know that there are some yield values here that are not realistic. There are some very low speeds happening that are probably true, but probably also causing issues with yield points. So let's just we know we're going to have to clean based on speed and yield at least. And also from a data wrangling standpoint, again, data wrangling is going to be with you every time you have data, regardless if it is geospatial or not. So the same happens here. So if you just think about it, you know, at least myself, what I'm proposing that we do as far as data wrangling is to, again, standardize column naming conventions. Again, we see this is a real data coming from a real field. I did not make this data up, but we see that, like, you know, we have some differences in how the column names are given. It's not hugely, you know, impactful, but it's something that it's a habit I like to keep, is just standardizing column names. I only want to select the columns that we need to keep going with this analysis, which again, we already talked about, were speed, dry yield, point X, and point Y. I want to rename the columns speed and dry yield to contain their units. I think it's really, really important to have units in column names so we know what we're dealing with. And even if we hand this data to someone else, it is at least intuitive to them what these columns are. Because right now, speed, I can guess what speed is, what units is speed, but I don't know yet because the data doesn't have that. Same thing with dry yield. I can guess based on the values that is pounds per acre, but it could have been something else that, you know, I don't know because the column name right now doesn't have that. And then create columns in the metric system. After we do all that, we really need to transform this data frame into a geospatial data frame. And then finally work with the projection of this data. So let's get started with that. If you come to the next chunk here on the wrangling, so I already left you some code. We're going to create this new object called yield17w. So we're starting with yield 17, which is what we've been working up until now, adding a pipe and cleaning names. So I already left you that. The next thing that I want to do here is if you add a pipe right after the clean names and go below the comment of selecting desired variables, we want to do a select here. So if you recall, we do select coming from the dplyr package. And again, as we start working with geospatial data, it becomes even more important that we do the dplyr : to make sure we're calling select from dplyr, because there are some geospatial packages that also have a function called select. So here I want to get, well, and perhaps I should just print this. So now, now what is coming into the select is the result of yield and clean names. Just want to print this to you so you can see. So now all the headings are lowercase. Just to remind you, because we need to get the proper column names at this level to do a proper select. So I want to select speed. So speed is lowercase. Add a comma, hit return just to break the code. I want to select dry yield, which is just like dry underscore yield. That's how it is now in this data set after going through clean names. Add a comma, hit return. I want to select point underscore X, comma, return point underscore Y. And also something that we did in the past, and I would just want to show you again, is the function select lets you select the columns, but also allows you to do some renaming of those columns on the go. So I want to come back here to the speed, and I want to say, I want to start typing speed underscore mph for miles per hour. So basically we're selecting the column speed, but renaming it to speed underscore mph, miles per hour. And on the dry yield, the same. I want to go right before dry yield and type yield underscore lbac for pounds per acre, say equals to dry yield. So again, we're selecting dry yield and then renaming it to yield pounds per acre. If you run this and you print the object on the bottom here, now we should have exactly that. We should have a column called speed and miles per hour, yield pounds per acre, point X and point Y. The next thing that we're going to do is transform to English, from English to metric. So just add a pipe after the select. And I already left you the code. You don't have to type it. You just need to uncomment or comment off or delete the hashtags from it. I already left you the conversions there. It's already out there. If you just now run it and print it, you should have two new columns called yield kilograms per hectare and speed in kilometers per hour. Okay, so now add a pipe after the mutate and go below the transforming into SF object. So this is going to be a really important function that we have not seen yet.
Hey, folks. Two of us consistent are getting an error when we commented off that code portion, and I'm not really sure why.
What does the error have? Some sentence saying something?
It just says error and mutate.
It says that problem was while computing yield underscore kilograms per hectare equals yield underscore pounds per acre times the conversion.
Okay, so it is possible, a couple of things to look for. One is make sure you have the pipes, right? So make sure you have that pipe and this pipe here. Another thing is maybe it could have been that the way you named your yield pounds per acre on top is not matching this one. So make sure it's matching exactly. So like, even though I say in words pounds per acre, but it's not plural. So make sure you don't have an S there.
See, mine is saying that object speed underscore miles per hour is not found.
Okay, so check the same here then. Because so what happens is we are creating the speed kilometers per hour based on the miles per hour. Okay. And the miles per hour we renamed on top here. So if you did not rename here, so if you left just like that, or maybe you rename to something that is different from what I have, that's what would be causing.
Okay.
Were you able to find the?
Yes. Did you get your email?
Okay.
Hold on one second. Miller hadn't got his yet.
Okay.
And
also just to, I mean, while you guys are trying to figure out, I just want to point out that every time you have a pipe, the code will be expecting to have something afterwards. So let's say if I were troubleshooting what we're doing right now, but on my side, I would have to delete this last pipe here because at this point, there's nothing coming after that.
It's all green to use the mutate.
Did you put a?
So I think I'm gonna keep going, but I can definitely help you after class. I mean, we only have 5 minutes, so we're not gonna miss a lot. But I can help you after class if you still have the issue. Okay, so so if you come to the end of the mutate now and you add a pipe there and you come below the transform into SF object comment, the function that basically, so right now, up until this point, this is a data frame, right? It's a tibble, which is also, I mean, you can think of a tibble as a data frame. It's not an SF object. It's not geospatial yet. So for us to transform a data frame into a geospatial, well, first we have to, in this case, we have to have the column that has that geospatial information, which is point X and point Y. But now how do we tell R that these are the coordinate columns? So to transform from data to SF, there is a function called st_s_SF. And inside of this function, there's a argument called chords, like this. So you say chords equals to, and then we need to give it what are the two columns that have the coordinates. Because we need to give two columns, right, X and Y, we need to use the concatenate function or the C function. So we do C, open and close quotation marks. We give it what's the column that has the X coordinates, so point_X. We get outside of the quotation marks, add a comma, open and close another quotation marks, and now give it the point Y. Okay, I just want to leave it again. Make sure that you're using the C function. Make sure that point X has its own opening and closing quotation marks, and point Y as well. Make sure you close all the parentheses in the end. If we run this and print now, look at what we have. If you remember, when we had an SF object, when we print it, it prints two panels, right? So the first one is talking about the geospatial side of it. So it's saying that it's telling us that it is a point shapefile, which it actually is. It's telling us what's the bounding box. So what's the minimum, maximum of X and Y, and what's our coordinate reference system. In this case, it is saying NA. But also one of the beautiful things about SF is that they combine the geospatial with the data. So we also have the data just like before, except that now we have a column called geometry, which is where the geometry of the geospatial data is found. Okay. So here's a really interesting point. In the previous exercise, when we're working with NAS data and using the county's shapefile or county polygons, maybe you recall this, but the CRS, when we printed those county vector data SF file, CRS was saying WGS84, right? So here it's saying NA. And the reason for that is because we did not provide yet an information to this data set of what is the native CRS of this data. I can tell you that it was WGS84 because of the values. If you look at the value ranges, it kind of makes sense that it was WGS84, but also because probably all, or at least most of the yield monitor data on combines use a GPS to record data on WGS84. So assuming WGS84 is a pretty good assumption. However, we have to, sorry, somebody want to say something?
The intuition of their voice, were they like the last student to do, or what were they? When they were,
You cannot hear me?
X and the Y. The intuition of the point X and the Y. Well,
Yes, what about that?
Well, was it like last student longitude points?
So where is that coming from? Is that what you're asking?
Yeah, what did they mean? What does that point mean in terms of units before?
Yeah, so the point X and point Y columns are coming from the GPS that is on the combine. that is collecting the positional data as yield is being collected as well. So every time they combine, yeah, so they're longitude and latitude, that's right. And that's why WGS 84 is, right, is coordinates in longitude and latitude degrees, or degrees of long and lat. So I just want to finish these two last pieces here before we end class today. I know we're already at 10, but let's just go for a few more minutes just to finish this. So how do we now come here and tell ARC that this object was recorded on WGS 84? So add a pipe here at the end of that STSSF function. Come below on the setting native CRS. We're going to use this function called st underscore set underscore CRS. So we are setting the native CRS. So let's say this data was recorded as WGS 84, but I wanted to use this as projected UTM. I should not give here the projected UTM CRS because it was not recorded as that. It was recorded as WGS 84, and that's what we have to first set it to what it was recorded and then transform to something that we want. So here to set it to WGS 84, go inside of this function. It has a argument called value. So this is the value of the coordinate reference system. This is the EPSG value of the coordinate reference system that we talked in one of the lectures that we started. So if you recall, the EPSG value for WGS 84 is 4326. If you run this and we print it and we come on so the data remains the same, but on the first panel here, where before it said CRS NA, now it says geodetic CRS WGS 84. So we successfully assigned the CRS that was used when the data was recorded, which was WGS 84. However, because we're going to be doing some interpolation in the future with this data, I do want to change this to so remember WGS 84 is degrees. I want to have a CRS that is metric, that is actually not an angle, but a distance measure. So with that, we want to change this from a geographic, oh, sorry for the typo there, geographic to projected coordinate reference system. So to do that, add the pipe, come after the transforming from geographic to projected comment, and we're going to use a function st underscore transform. So we are transforming the CRS, and inside of it, it has an argument called CRS that we're going to use the EPSG value for NAD83 UTM zone 16 north, right? Which again, if you recall that lecture that we talked about this. So the EPSG value for that is 6345. Before I run this, I just want to remind you again that before running the ST transform, it was saying geodetic CRS WGS 84, which is again a geographic reference system, meaning that it is in degrees. Now, if I run after the transform and I print it, you see that now it says projected CRS, so not geodetic anymore, NAD83 2011, UTM zone 16 north, right? So these pieces here, these last three functions of the wrangling flow were really specific to a vector type of file that inside R is treated as an SF object. Okay. So I think we can stop here today. Someone had a question?
Yeah, it's me. I have a question. So where can we get these codes, like value is equal to 4326, CRS is equal to 6345? How can we access these if we need in future?
Right. So these, so there's a website called EPSG something. I mean, if we Google it, it's pretty easy to find. So I'm just bringing this over my browser for us to look. EPSG codes. Yeah, so I use this one here called epsg.io. is one that you can really explore this in a lot of ways. You can find different EPSG values for different coordinate reference systems around the world. So if you recall here, let me just bring this back. WGS 84 is a single EPSG value for the entire world, regardless where you are. However, UTM NAD 83, if you recall from class, each band in the world has its own EPSG, right? So this, if you go, even in the US, if you go to, I don't know, Alabama, it's going to be a different one. WGS 84, the same regardless where you are in the world. If we're doing UTM, it's going to be different. Okay, I think we can stop here today. We still need to finish this exercise on Wednesday, and we're going to start the next step as well on Wednesday. So we'll be sharing that script maybe tomorrow through GitHub as well. Don't forget to submit your assignments by today, 11:59 p.m. I guess that was it. If you have any questions or issues with the code today in class, feel free to send me an email and I will send you a Zoom link shortly for us to troubleshoot. And if not, I'll see you all on Wednesday.